Hello, welcome once again. This is my third take at trying to tell you what I know about symbolic mathematics and from engineers, MATLAB 4, Yoda work I did. First one I didn't like the way it started. Second one, somebody interrupted me 8 minutes into my presentation. Once then, when I paused the recording, and when I got done, I restarted and was chatting away to myself for 20 minutes when I looked down and noticed that there was still only 8 minutes on the recording. So rather than trying to figure out where I was, I'm just starting over, and this is the last time. So for better or worse, this is what you're going to get. Okay, so now that we got the pleasantries out of the way, this is Chapter 12, Symbolic Mathematics for MATLAB for Engineers, written by Dr. Holly Moore. 6th edition. Okay, cool. So, good golly, Miss Molly. Here we go. So what you're going to learn in this chapter is how to create and manipulate symbolic functions, factor and simplify mathematical expressions, solve expressions, solve system of equations, and create and use symbolic functions. Chapter sections 12.6, 7, and 8. I will not cover because we don't cover that, and it's not a prerequisite in our course for this course. That is the calculus abilities of MATLAB. I highly recommend that you take some time and browse through it, look at the examples, whatnot. When you get into your calculus courses, it would be great for you to use for a check, not to do your homework for you, but to check your homework and make sure you've done things right. Oh, sorry, cat. I'll move my foot out of your bed. So, yeah, and then there's one in here that's not listed, and that's converting symbolic functions into anonymous functions. And if that doesn't cover it, I think it covers it at the very end of this PowerPoint. If it don't, I'll cover it on my own. I can do that. I'm the teacher. Okay, so onward. Introduction. So, MATLAB's symbolic toolbox allows you to create symbolic arrays, which you can use to manipulate and solve symbolic expressions and to evaluate them numerically. It allows you to take the portions that we're not going to cover, take derivatives, do integration, and perform linear. But we will cover linear algebraic manipulations. And then the more advanced features, Laplace transforms, Fourier transforms, and variable precision arithmetic. If you want to learn on that, go ahead and take a look at it. If you got questions, send me an email in Canvas, and if I don't know the answer, I'll make one up. I'm good at making things up. Okay, so the symbolic toolbox should be an add-on that came with your student version of MATLAB. If you don't have it, we need to get you into MathWorks and locate where we can download it and attach it to your MATLAB, because you will need it for this course, for this chapter. If you have a professional version that you got from somewhere else, you'll have to buy the symbolic toolbox. It doesn't come free. Okay, so symbolic algebra. Symbolic mathematics is used regularly in math and engineering and all your science courses. It's basically what you've been learning since pre-algebra. It's taking letters and numbers and mixing them together and solving the mysteries of life. MATLAB just gives you a way to do it on a computer. It's generally more gooder to solve your problems algebraically before you substitute values, because there's always a possibility of dropping a digit or a sign or some silly thing. I've done that, because I are stupid. So more gooder to do it symbolically before you start plugging in numbers. Okay, so consider this equation. First glance, it looks complicated. 2 times x plus 3 squared divided by x squared plus 6x divided by 9. However, if you remove the exponent, you notice that, oh wow, that top stuff is the same as the bottom stuff, only multiplied by 2. So it boils down to 2, right? and that's the answer, right? Kinda. I mean, if this is the equations that you're working with that model what you're doing, there is a specific case where you could lose some information, and that would be at -3. Because if x is -3, the equation is totally undefined because you're dividing 0 by 0. Okay, so just be aware that when you're doing things, it's more gooder to use full equations rather than sometimes the reduced form. Okay. So MATLAB's symbolic algebra capabilities allow you to perform the simplification or manipulation, manipulate the numerator and denominator separately. Okay. So another great capacity of the symbolics in MATLAB is that it can manipulate your equations to solve for other variables. This equation you should recognize from the homework. We've come across it several times. And if you wanted to solve that for t, I mean, I think I could probably do it, but I'm sure I would miss something like perverting k0 over k when you're taking the negative logarithm of q over rt. So that's where MATLAB comes in handy, and it'll do all that nasty stuff for you. You just have to say, okay, cool, I entered it in right, and so MATLAB spit out the right answer. But make sure you check, make sure. Okay, cool. T. Okay, so here's how you create some symbolic objects in MATLAB. Before you can solve any equations, this is necessary to do that. There are several kinds of symbolic objects that we'll be using in MATLAB. There's simple variables, simple expressions, functions, which are basically kind of an expression, and equations. Now you're thinking, well, they're all equations. Okay, well, hang on to that opinion until we get to the section on equations, because it'll just mind blown. Okay, all right. So, Sim versus Sims. I was on this tile when I got interrupted and I paused everything and forgot. So hey, look, I'm a minute ahead of schedule because I was 8 minutes onto this tile. Okay, so if you're going, you can define your symbolic variables in two ways. You can set a variable equal to a sim character, so that this will place this character in X, or you can just do sims with an S X, and it'll do the exact same thing as all this stuff up here, but it does it in a much simpler form. And back in the olden days, when I was knee-high to a grasshopper and was taking Pascal and C, this is how we did all our variable declarations. It was the type of variable, and then the variables and you can list as many variables over here as you want, separated by a space. So this is what we did. This one, I think you would have to do each individual variable. I don't know, you might be able, I can't remember if I don't use this one. I use this one. This one's so much easier. When you're a hunting pecker, I mean, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 counting the spaces, and down here we're 6. So it's half of the character types. That's about 100,000% less possibility of me making an error because we're so stupid. So this is and in a minute you'll see a big red box come around here. But both techniques give you the same results. The best strategy is to, the first strategy, okay, so I've already covered that. This all does. So here we go. Most programmers, this approach is most straightforward, and you should default to this approach. This is the more gooder approach. Trust me, it's more gooder. Okay, so in symbolic expressions, you can create symbolic its expressions by using symbolic variables on the, like here, y was not defined as a symbolic variable, but it was created using a symbolic x. Therefore, you look over here, y is symbolic. And you'll also notice that MATLAB does not indent the results from symbolics. I think that's done that way so that you can more easily tell when an equation is written in symbolic format rather than a numeric one. I mean, to me, that's the only. But then, you know, I don't know everything. I don't know anything. But that would be my guess. Is so anyway. So yeah. So it's symbolic. Okay. Oh, here we go. Flippy, flippy, flippy. Do not use the array operator when writing. Okay, that's a good thing you did flippy, flippy, because I would have skipped that. Basically, that means that if you're raising a power, you don't use the dot element. Okay, you don't put that little dot caret, dot times, dot divide. You just write it as if you were writing in an algebra class, 6 times x. The symbolic functions in the MATLAB will take into account whether it's a scalar or an array input to the function or a variable or what the calculations it's doing. Okay. Symbolic functions are created using a similar approach. Up here we did sims. We defined this as a function with inputs of y and z in all symbolic format. And so here, then we come down here and write our equation. It doesn't have to be named fun. You can name it whatever you want. You can name it Kalusahatchee if you wanted, if you could spell it correctly each time you used it. To me, this would be a lot easier to spell. But it's just like any other function in MATLAB now that it's done. The only difference is the output is going to be in the symbolic output. So everything there is symbolic. Is that cool or what? Say, yeah, man, that is just mind-blowing. Okay. Yeah, see, so here we go. We plugged in 3 and 4 into this function, and it returned 34, but it is a symbolic number. It's not, you can't just take that now and do some kind of calculation with it. It's a symbolic character. You can convert it from symbolic to a floating point number. I know there's a slide coming up, like 4 or 5 slides from now, but I'm going to give you a little sneak preview. To convert this from a symbolic number to a double, just use the double command. Do double answer, and that will change from a symbolic to a double. Okay, cool? Yeah, far up. Symbolic variables can also be used as inputs. So if we created symbolic A, symbolic B, and put them in there, one advantage to doing this is you could set the output to this equal to another variable, and then this equation would be assigned in symbolic form to there, and this would still be in its regular XZ form. So they were created in name sims and the command. Okay. Creating functions in one step. You could do this if X is predefined as a symbolic. You could do this all in one step, which you know, I should put that in here, but it just seems to me like, isn't that what we did here? We created this as function as symbolics. I mean, I guess if we'd have just created X and Z as function, not function, as symbolics, then this would have created that as a symbolic function as well. Okay. Okay. So symbolic equations. This is the equations part. Okay. This is not an expression. All this back here. Give me the back button. Here we go. So this is a function. It's not an equation. Let's go back. This is not an equation. This is an expression. Okay, an equation is this. This is the variable name to which we are creating, and we're giving it this equation. And you should recognize that from your engineering courses, that is the ideal gas law. PV equals N. There's the N right there. RT. So that's the end. So the double equal sign, or what does she call it? I've always known it as the comparison, because you're comparing variables. But you use a double equal sign, then that makes that an equation. So the ideal gas law is this. Why is that important? We'll get to that in just a minute. I think. I hope. Okay. Got it? Got it. Okay. Yeah, ideal gas law is the assigned name. And then everything after it was the equation. So we just learned three. Oh man, I forgot to go fix this slide. So we just learned three approaches to creating symbolic objects that store entire expressions. So first was the expression. This is just an expression, and this needs to be indented over here, but it's not. It needs to be. So this this is an equation here, and we assigned it to that, and this is all. But it's not an equation; it's an expression in symbolic terminology. So the second is a function. This is a symbolic function, and it's in a type of an expression. On to the last one would be the equation. Again, an equation has the double equal sign with the equality operator. That's what she calls it, equality operator. So that makes that an equation. Okay, trust. If this is going to get make more sense here in just a minute when we get into some of the manipulating of these symbolic stuffs. Okay, and this really needs to be indented over into here to line up with all this other stuff. That drives me nuts. Okay, so recall the equations are not equal to something. Most of the time you will be working with either simple symbolic expressions or with expressions in the form of symbolic functions. And many, but not all, of the MATLAB's functions designed to manipulate symbolic equations work for both equations and expressions. Most, but not all. And there's an example coming up here shortly. Okay. Am I still recording? Yeah, okay, I'm at 16 minutes. Okay, so now we get into, well, what do we do with these symbolic equations? Yeah, they're cool. They write it down, and it gives you a nice little equation, but what do we do with them? Well, here we go. The first thing we're going to do is simplification. Okay, MATLAB automatically simplifies an equation when you put it in. Okay, if you're collecting data and you find, well, I got an A, oh, I got a 2A, oh, I got 3A minus, or A minus 3 squared, and then all this, these are different inputs. You don't have to combine them by hand before you enter them into MATLAB. You just put them down there as you got them, and poof, it'll automatically combine. Not fully to its most simplest form, but it'll combine it down and make it look more gooder. So Z has been combined from this down to this. However, we can go one step further and use the simplify function, which if we use a simplify function on this will expand this out, subtract that out, and leave you with a grand total of 8 minus 5a. So, it would have taken me probably an hour, maybe 2 hours to combine all that together, and I probably would have got 36 minus 17a squared. Okay, so maybe, oh well, anyway, but MATLAB did it in two short lines of code. And you could have done you could have put the simplified in here and made easy equals to all that. So, but yeah, cool, huh? Right? Yeah, sweet. Okay. So simplify also works on functions. If you created a function with things out here that are not in the smallest form, it will simplify it into remove everything, and cool, yeah. And it also works on equations. So if you create an equation like this, it would woohoo you too. It would simplify it and make it look more clean and hunky and or dory. Hang on, I'm going to turn that thing off so that don't do that no more. I don't like woohooing in the middle of my presentations. Yeah, I know you guys are used to them. This is the 11th. No, 12th. This would be the 12th because 13th because we did 2 exam reviews. Whoa, you guys are getting special. Okay, anyway, so it works on equations as well. Simplify works. Cool. So some of the other functions that are available to work manipulate the symbolics is the expand. It will take and expand out all portions of the expression or equation and just bring it all the way out. Factor, it can take the equation expression and factor it if it's factorable. It'll collect all like terms and it'll combine products of powers as a single power. And then this last one here is if you have a big equation that has a fraction, this will tell you what is in the numerator and what is in the denominator. This does not work on equations. This only will work on expressions and functions, because the function is a form of the expression. Okay, cool. You got all that? Okay, cool. See you next week. Oh, no, wait. We still have 40 slides to go. Oh, 40 slides. Okay. Solving expressions and equations, section 12 deuce. This is where we get into some of the power of symbolics in here. You can use a symbolic to solve equations, to find the roots. You can put numbers in and find answers from the numerical inputs. And you can also solve for unknowns symbolically. You know, if you got an equation you want to in terms of x, but you want to find what it is in terms of t, it will solve that for you. Oh, we showed that earlier, but yeah, so cool. Can also solve systems of equations, linear equations and nonlinear equations. Whereas MATLAB in the numeric world can only do linear equations. Cool. So the solve function. You just you solve, input your equation. It's got to be symmetric, not symmetric, symbolic. There we go. So this is a symbolic expression of x minus 3. When you put E1 into solve, it automatically sets this equation equal to 0 and solves for it. And obviously 3 minus 3 is 0. So that was one of the roots. And then here we have x squared minus 9, and we're solving for that, which is plus or minus 3. And you notice that it is a 2 by 1 answer, even though and again, these look like they're just numbers, but they're not. They are symbolic characters. If you want to make them real numbers, just use the double function command. I use those interchangeably, so please don't get confused. So just do a double on it, and it'll change it from sim to double. Cool, right on. Okay, so if you put in here an equation or expression that has multiple characters, a, b, c, and x, MATLAB will default to solve for x, or whichever is algebraically closest to x. So in this case, there's an x, so it solved all these equations for x. Had x not been there, then it would have solved for c. Okay, so solving the quadratic equation gives you this formula, which you should be familiar with. If you want to solve for a specific character in here, we want to solve that for a, then you just do a comma a. So now it's going to solve this equation for a, which that's the equation. Okay. Solving equations. So there's two strategies to solving equations in MATLAB using symbolics. The first one is you take everything on the right hand of the equation and move it to the left hand by subtracting from both sides, or adding if it's negative. The other option is to use the equal operator, which is the double equal sign. For example, here is 5x squared plus 6x plus 3 is equal to 10. Using the first method, we subtract 10 from both sides, and it becomes 5x squared plus 6 minus 7. Oh, 6x minus 7. Then you can plug that in and solve it. Or, okay, so here is doing that. So we collected everything on the left side and did the solve on that, and we get this for an answer. Or if we do the other way, set this up as an equation with the double equal sign and put that in to solve, we get the exact same answer. So you can do it either way as you like. Again, I prefer this way because I could probably subtract 10 from 3 and get 9. See, now I don't know if I said that in this recording or if that was in the previous recording, but yeah, I need a calculator to add 2 and 2 together. That's, wait a minute, 1, 2, 3, 4, 4, 4. Okay. Yeah, so 2 approaches. Whichever one makes you more happy, you're more than welcome to use. Notice that the results are expressed as simply as possible using fractions, but you can get a numeric value out of that by doing double. See, I gave you a sneak preview of that, so here it finally is on slide number 27 of 65. So that's how you get numbers out of that you can actually use for calculations. Okay. Solve function can involve a system of equations. Okay. So yeah. So when you use the symbolic toolbox to solve system and linear equations, if you do not assign the output to more than one, well, if you just assign it to a single variable, the output will use the structured array, and to get the results out of the array, you would have to do the dot syntax. What is that? Well, here it is. So this, we have 3 equations, 3 unknowns. We set the output from the solve function. And again, to solve system equations, you write your symbolic equations, 1, 2, 3. Make sure you have 1 for each. Put them in here in the parentheses for solve, and best to set it equal to a variable. If you don't, then it just defaults to ands. So this is now a structured array with the fields of x, y, and z. To pull those numbers out, you do the answer, which is your variable name, dot, and the variable that you want, x, answer dot y, answer dot z. And that's how you pull them out of a structured array. Now there is a method to which you can get these without using the structured array, and that is to assign the output from the solve function to 3 variables, x, y, and z, and it'll pop them out. Now the only downfall of this method is if these are currently in alphabetical order, if this was C, Y, and O, it would be C-O-Y. So just make sure you're using the right numbers when you're pulling them out of the results. I'd hate to have you pull the wrong number up and have an airplane crash because you picked up P instead of Q. Okay, cool. So this is where I got to before I realized I wasn't recording last time. So anyway, so using solve function for multiple equations has both an advantage and disadvantage used in linear algebra techniques. In general, if a problem can be solved by means of matrices, the matrix solution will take less computer time. However, linear algebra is limited to first-order polynomials. To solve functions may take longer, but it can solve nonlinear problems and problems using symbolic variables. And then table 12.2 lists some of the uses of the solve function. Now, when you go to page 540 or 485, whoa, dyslexia hitting me big time there. I did make a post in Canvas. There are typos in that table. It just whenever there was an equation, the double equal sign has a space betwixt them. If you try typing that into MATLAB with a space between the double equal signs, you'll get an error. So just be aware that if you're typing that in, and don't make yours look like that. There should be no space between the double equal sign. Okay, so subchapter sub 3, substitution and symbolic functions. Once the symbolic expression is defined, we can substitute numeric values into it and have it do the calculations and spit out an answer. It doesn't always have to be a numeric. You can also spit in some other variables. This can be accomplished using the subs function, and or you can create the expression to a symbolic function. So the sub function is usually used if substitution only happens once, or if it occurs as part of a larger process. So something that you're going to do repeatedly over and over and over, it's best to create a function with those substitutions already made. It's not saying you can't do that. It just, it might be more gooder programming style to create a different function rather than substituting over and over and over. Use substitutions will be performed repeatedly. Yeah, see right there. Cool. Okay, so using the subfunction. So we created an expression here of ax squared plus bx plus c. That's an expression with symbolic ABC. So now we take that equation and we created another variable y, and we're going to substitute in E4 all the places where there's an x, the new variable y. So now it's a y squared plus by plus c. So that just took this equation, left this equation as is, and created a new equation, and because we've assigned it to a new variable, it's a new equation with y's instead of x's. So that's the gist of subs. I mean, it's you can, like I say, you can do numbers, or you can do other symbolic equations. So here we've took that same equation, and in place of x we put a 3. So now it's 9a plus 3b plus c. Now if you want to get really neat, you could, the original expression remains unchanged. So again, I said that on the last one. So now let's substitute everything. Let's get rid of our constants a, b, and c. So in square brackets, we're going to replace a, b, and c with, in square brackets, 1, 2, 3. Poof, now we got just x squared plus 2x plus 3. Neat. And then you can do another subs and say for values of x equals 6, your E6 sub, and then what are the values for x you want, and it'll solve the equation for you. Cool. Yeah, see, here we go. So we have some numbers 1 through 5. Again, here, so see, here's a vector. Oh, sorry. Well, it is a vector because it's numeric. But this is an array of numbers of 1 through 5, substituting in everywhere it sees an x in E6. And it returned an array of calculations as if it was a dot element, a dot multiply. So if you plug in 1, 2, 3, 4, and 5, you would come. I know you would, because I did this yesterday when I was reviewing this PowerPoint piece. So yeah, but again, remember that this is symbolic. If you want numbers for calculations, you need to convert it to a double. Like, I probably could do it to a single too, but you know, programmer's choice, I guess. Okay. So here we go. Creating symbolic functions. You can use a function to convert an existing expression stored as a variable into a symbolic function without retyping any of the code. So, so here we created symbolic characters a, x, and y. We created an expression of E7, which is x squared plus y squared, and to make it a function, it requires 2 inputs, a symbolic expression and an array of variable names. So G is, now this is going to be a function from the expression E7 with the variables x and y. So now we have a symbolic function G with the inputs x, y, which equals x squared plus y, and you put numbers in, and cool. Cool? Say yes, man. That is, okay, you guys are just getting tired of hearing that, so I'll stop. Okay, so section 12.3, symbolic plotting. You'll remember back in the early days when we learned all the plotting commands, there was one called fplot. Well, this is where symbolics, the fplot shines, is with symbolics. It was introduced, an example is that this is an overloaded function, which means the same function used for more than one application. The MATLAB program decides which is appropriate based on its input. When the symbolic information is supplied, when you send it an expression or a function, it uses the symbolic plotting tools. So the F plot automatically plots your function in a range of -5 to 5, so you don't have to input the range for this to work. You can input if you don't want -5 to 5. You can change that by putting in whatever range you are looking for, and it automatically selects X to be the variable, and it uses that variable and creates enough data points to give you a nice smooth curve. And then if you want annotations, you have to do that the old-fashioned way, one at a time. X label, Y label, title, and if you're using the tiled layout, then yeah, the whole thing. So here's an example. We created X as a symbolic. We set Y equal to X squared minus 2, and then we just did F plot 2. Poof, that's all we had to do was F plot 2, and we get a chart, a plot. Okay, there's no labels, titles, nothing, but we didn't have to specify the range from 5 to 5. It just automatically did that for us. So now if we want to specify a wider range from -10 to 10 and add a title and X labels, we just add that, and poof, there we go. So now it goes from -10 to 10. It's got an X, a Y, and a second order polynomial title. So that's pretty much what we were doing before, just a little bit less stir work. So implicit plots, so F implicit, if you have an implicit function, it allows you to plot these. For example, the equation for a circle, which is X squared plus Y squared, is equal to 1. So this allowed us to do that, and we specified the range from -1 to 1, well, -1.5 to 1, and so that created this plot for us. The circle could also be done parametrically. The parametric plot is basically plotting one function against another function. So F plot of sine of t then against the cosine of t from 0 to 2 pi, confining axes to plus or minus 1.5, gives you basically the same image. Okay, cool, right? Yeah. Okay, so here's some additional symbolic plots types. These are all in the textbook. One of the pages in there, I don't know where it's at. So for numeric plots, you got plot, plot 3, mesh, surf, contour, and polar plot. In symbolics, you have F plot 3, F mesh, F surf. You see a pattern going here. It's like we're adding an F. That's my final grade to me, because I did lousy this semester. I'm sorry. The only difference would be this one here is a polar plot versus easy polar. So if you're doing symbolic plots, you basically just put an F in front of the commands that you're already used to. And then also the symbolic plots has the implicit and the F implicit 3, which does a 3D plot. Okay. Oh, now this section, this is cool. I was going to try and find my earlier textbooks to see if this was in it, because I don't remember this, but this section is really cool. This takes me back to the days of Maple. I don't know if any of you are familiar with Maple, but it was a really cool program, and in it I could put the units on my equations, and when I would multiply my equations out, they would carry the units through for me, and then at the end I would know a number based with the units, and it was really, really cool. But this goes even one step further. Calm down, take a deep breath. Okay, so units. MATLAB has this really cool thing where it can add units into your equations for you. And we'll get hopefully, yeah, it's coming up. It's cool. Sorry, calm down. So yeah, so some of you have experienced this in homework already. Some problems you had was the units didn't match up, and so you got, I mean, the code was right, but it was wrong because of the units. So this will allow the user to check for consistency. Do unit conversions. I mean, that right there in itself is worth every penny that they put into that. Because if you assign, like, if you're multiplying meters to feet, the response will come up with the answer of meters to feet, but then when you do some prestidigitation to it, it'll convert that for you and give you the final unit that you're looking for, and it's really cool. Include important physical constants and calculations without entering them directly. So yeah, so units is really cool. I really need to find my earlier textbook to see if that's in there, because I don't ever remember us ever talking anything about units. That may be new to 6th edition. So in order to get units into your MATLAB, you have to do this sim unit. You can assign that to any variable you want. Holly just used U for units. And so this shows you 7 basic units that are available: the ampere, Kelvin, kilogram, meters, mole, second, candela. But there's more than that. I mean, you can hit this through all units, and it'll show you everything that's within there, and it's really, really, really cool. Well, how do we use it? I want to get in and use it. Show me how to use it. Okay, hang on. Control yourself. I'm controlled. Okay, so yeah, we've already covered that. So in order to use the units, you take the variable name that you assigned it to, and then use the dot syntax. So this is .m for meters, if you put in one that doesn't, well, here you can guess, but there's a better approach. Okay, so yeah, so you put feet, but there's a much more gooder way to do this. Once you hit the variable name and the dot, a little window. Now my window is differenter than what's in this picture. I think it's because I got a different version of MATLAB than Holly did when she wrote this, because, well, I don't know, that's saying 22A, I'm in 22B. But still, mine was a little different. But still, you can type in feet or foot, and you know, it'll pop this window up. You can scroll to find the unit you want and then accept it. And then see here, so we've got 5 meters up here, 10 feet down here. We multiply them together. That's a half times meters divided by feet. Well, what unit is a meter per foot? So it's a half meter per foot. So they're not automatically simplified. Now that's one downfall of the system, is it should be automatic. I'm lazy. I don't want to have to do this extra step, but still, it's there. It's cool. To get the conversion from units, just do simplify and your variable, and then it'll take it out and bring it into why doesn't it show which unit you're in here? I thought that it did. I'll have to look at that. So anyway, and then if you do a double on that, it'll bring it to from a fraction. So I have to. Okay, I played with this yesterday, and I thought it gave you an answer when it did the final conversion, but the book's not showing, or not the book, but the slide's not showing that. So I'll have to look at that, and I'll let you know what I find out. So here's some more complicated analysis. The units were combined, canceled, and so yeah. So here, you got all these different units in here, and you multiply them together, and the ones that canceled out, it automatically canceled out, but you're still left with feet plus meters. Again, and then you'd use a simplify. Okay, so now see, this one has the units in it. I don't know why that last page didn't. See, I told you, I'm only half as crazy as I think I am. Okay, maybe not quite half. So anyway, so using the simplify, it kept it and put it in feet. MATLAB chooses which unit to use. So you know, and if you don't like it, there is a conversion which you can use right here. Unit convert, the number, the variable you want to convert, and to which unit you want it converted to. So. yeah, cool. I'm not losing my mind. Yay. Okay. So if you get your results and oops, and it comes in with a unit, but you don't want the units for you can separate them out. Okay, so here the total was whatever that number is, meters. Well, I don't want the meters anymore. I just want this number to go on to my next calculation. Well, you can do separate unit, and it'll separate it out. If you assign it to two variables, the first one will be the value, and the second one will be the unit, and then you could double the value to get a number that that converts to. So yeah, cool. Right arm out of state, farm out. Oh boy. Okay, so one thing you have to be careful about in using units is in temperatures, because a lot of your calculations you're dealing with has a change in temperature and not an absolute temperature. So here, if you're saying 5 degrees Celsius, is that a change in 5 degrees Celsius, or is that actually 5 degrees Celsius? I mean, that could be 150, the difference between 150 and 140 degrees Celsius, which is a lot different than 5. So this will convert from obvious, well, not obvious, but it'll convert from one unit to the next. But if you want to know the actual temperature at that point, then you have to use these properties in here. So you just put in temperature and that you want absolute, and then it'll do everything in an absolute calculated value. So just be aware of that if you're using the units in temperatures. Calculus, again, the MATLAB has a great functionality in calculus, finding the derivatives, the second derivatives, doing integrals, boundary conditions, and all that other kind of stuff. If you want to check it out, and if you have questions, by all means let me know. If I don't know the answer, I won't make it up, I promise. I will seek out the answer and get it to you. But yeah, and it even gets into partial differential calculus and some of that really more advanced calculus, but it's beyond the scope of what's required for taking this course, so we just don't cover it. Okay. So the one thing that wasn't in the first page was converting symbolic expressions to anonymous functions. If you remember, an anonymous function is written inside the main script file of your M code or live editor. And so to do that, you create your symbolic equation and then put it into MATLAB function. That is the name of the function right there, and it'll return you an one of those anonymous features functions, f, which has an input of x and is the negative sign. So yeah, cool. Cool. Yeah, far out. It can also be used to convert numeric functions. So yeah, cool. Okay. Okay. So I guess I should keep going here because I still got 7 slides to go. I thought I was done. Difference between symbolic and numeric functions. So dy is a symbolic function and returns a symbolic result. G is a numeric function and returns a double result. So they're both the same answer, just this one is unusable for calculations. You'd have to do the double on that to get it to where you could get it down to where it says 0.0384. Okay, so summary. Toolbox required, comes with student version, sims command. Variables are defined. You can create expressions, functions, and equations. You can set them equal to something. Expressions are not. The equations are. You can find there are a lot of built-in functions for the symbolic toolbox, and then gives you the numerator, denominator, expand, factor, and collect are done with your expressions and whatnot. Simplify is really cool. It simplifies things down to make them look easy, cool. Solve, you can solve anything for roots or for any value you want, and for system of linear equations. Substitute, you can substitute into symbolic equations, and okay, and symfuncs and functions are type of okay. MATLAB works at sim unit. Now remember that sim, SYMUINT. Play with that. That is really cool to add and to convert between units. And then the plotting, the F plots automatically plots from -5 to 5, but you can change that, annotating the same way as in MATLAB plots. And this work is protected by the United States copyright laws and is provided solely for the use of instructors. That's me. Okay, so now what I want to do, I want to go through and I'm going to work a few of the parts of the practice exercises. I'm not going to do the whole thing. I'll just do what's necessary to try and get the concept. See if I can convey what's supposed to be done. Okay, so not current folder, workspace. So this is my workspace, so you can see what's what and who's who and however and whatever and whyever and whatever. Again, I like to have my results come underneath. Okay, so let's see if I can do this without causing problems with the computer. So practice exercise 12.1 says to create the following symbolic values using the sims command. I can do that, sims, and we want an X, an A, a B, and a D. That was the easiest part of the whole thing. Actually, and now if we run that, we see over here we got a whole bunch of symbolic stuff. So, okay, so I'll do problem number 2. I'll verify that each of the variables you created are listed in the works as symbolics. Hey, I did that already. Cool. Ahead of my time. And then create the following expressions. So we're going to have equation 1 is equal to x raised to the 2 minus 1. X2 is equal to, in the parentheses, x plus 1 raised to the 2, and then ex3 is equal to a times x raised, which one am I on? 3. 2 minus 1. 2 minus 1. ex4 is equal to ax squared plus bx plus c. A times x squared plus bx plus c. Equation 5 is equal to ax cubed down to d. A times x raised to the 3 plus b times x raised to the 2 plus c times x plus d. Okay, once ex6 equals sine of x. Okay, so there's all my equations, and we can run them and see. Oh, bx. I gotta have a multiplier in there. And you guys didn't say it. You watched me do it and didn't say a word. Wow, that's gratitude for you. Okay, so you can click on this for suggestions, approximate numerically, or do all this other kind of stuff. I'm not familiar with that, so you can play with it all you want. Go away. Oh, I didn't ask you to open. Go away. Okay. So there's practice exercise 1. Practice exercise 2 is on the next page, on page 479. It wants to multiply EX1 by EX2 and name the result Y1. So we're going to go, let's create a new section break here. So we're going to have Y1 equals EX1 times EX2. Boom. And there we go. Isn't that cool? Say, yeah, that is just righteous, dude. Okay, and then it wants us to divide 1 by 2. So we're going to go EX1 divided by EX2. Oops, and I was supposed to assign that to something to Y2. Y2 because I was told to. And so there's our equation. And then 3 is to use them den to extract the numerator and numerators. Okay, we can do that. I don't like everything being down at the bottom, sorry. It doesn't say to assign them to anything, so I'm not going to. Denominator, not denominator. You're an idiot. I know it. Thank you. Thank you. Thank you. From Y1 and Y2. So there's Y1 and num den Y2. Hang on a second. Oh, I gotta assign it to get the denominator, and okay, so yeah, it did tell me to. I just didn't read it right. Num Y1, comma, the denominator. In order to get the denominator, you got to assign it to two variables. Assign the output. So num Y1, comma, num, no, den, you're an idiot, thank you, and not Y1, Y2, you idiot. Denominator, Y2, square, equals. Okay. Okay. And then use factor, expand, collect, and simplify functions on Y1 and 2. What'd you do that for? Because I'm stupid. Okay, so we'll use factor, and I'm only going to do it for Y2. I don't need to do it for Y1. And expand Y2 and collect. I want my $2. And simplify Y2 and poof. So that factored is that, expanded out is that, collected and simplify in this case are the same. Okay, cool. So that was 2. 3, we'll do, let's see, okay, we'll do, why are you blinking at me? Don't blink at me. That makes me anxious. Okay, so 3, 1, we're going to use solve to find the roots of e equal, so we're going to do solve EX1, and there's the roots for that one, -1 and 1. Okay. Please find the roots of EX2 and to solve the equation. we don't have it, so I didn't do those. So I mean, we could do it for just for grins and giggles. EX2 -1, 1, -1. Okay, so solve function EX3 for both x and a. So solve EX3 for a. And I mean, if we want to do it for x, we just leave off the a. Okay, I'll let you do the rest of those. Number 4. Systems of linear equations. Cool. So we'll do a section break here, and since we're not using those equations anymore, we'll clear everything out. Use the following system of linear equations. Okay, so we'll start by defining our symbolic variables, which is going to be x, y, and z. X, y, z, and then I'm going to skip part 1. I don't need to do this using inverse. You all know how to do that. Define a symbolic equation representing each equation in the given system equation. Use solve function to solve for x, y, and z. Okay, so we'll go equation 1 is equal to 5 times x plus 6 times y minus 3 times z, and that's equals doubled 10. And equation 2 is equal to 3 minus 3 and 2. 3 times x minus 3 times y, and plus 2. Plus 2 times z is equal to 14. And then equation 3 is equal to 2 minus 4 minus 12. 2 times x minus 12. No, 4. See that? I can't even remember things for 2.8 seconds. Y minus 12. Oh, because I don't have a space here. There's one of my lists didn't line up right. That's the one that shouldn't, because it's a double digit. And this is equal to 24. Okay, so there's our equations, and we should be able to pop those out. See, it dropped the doubles and wrote it as an equation. So let's assign these to variables, not curly brackets, square ones, you idiot. Equals solve equation 1, comma, equation 2, comma, not 3, you got to put the EQ first. And voila. There's your answer. Cool. So if we want to see our structure, oh well, I didn't do the structure array, so I guess if we want to do this structure way, results equals all of this. I'm not going to type it again. That's too much. And then if we want to see our results, we would do results, no K in results, and an L before the T. Come on, you can do this. Dot X results dot Y and results dot Z. Oof. And there they are. And you'll notice still that these are all in symbolic. If we set this equal to A, it will still come out as a symbolic to get it to a double, we would do double A. And now we'll see that ants is, no, oh, because I didn't, don't tell me that, oh, because these, it was, and then I changed it, so let's set that equal to T, because the last one was an ants too, which overwrote the first one, making it, so where's T? Right here, so it's a double. It just shows where's my type. Class, there we go. There we go, class, there it is. Okay. So number 5 is use the subs into the expression equations, find approximate for x. Okay, so now we need to go back up here and rerun this one to get those equations back into memory, because it wants us to use those, and it wants to I'm just looking to see if it's specified what to assign it to. Equals subs, and it wants it into each one of the equations. I'm not going to do each one, I'll just do 1, comma 4. I think it was x, comma 4. Boom, 15. Woohoo! Cool. Okay, and so the next on is the practice exercise 6 wants us to do an F plot of our equation 1, EX1, from minus 2 times pi to 2 times pi. Oops. Hello, where's my plot? There it is. Okay. And then, you know, you can add all the annotations to it and whatnot. All that other cool stuff. The last one, well, it's basically the same as what we've been doing. It's just using the 3D plots. Anyway, hopefully this helps. I've kept you here for over an hour now. If you got any questions, give me a holler. I'm more than happy to help you out. Thanks.